very quick introduction. My name is Eric Pope. I'm the principal engineer and memory architect for HP's computer organization. I am an active participant in JEDEC, and I serve on the JEDEC board of directors. I've been working with memory in one way or another for about the past 25 years. And so I was asked to give a brief overview. Now, this is an hours-long discussion boiled down into about 15 to 20 minutes. And so there's not going to be tons of detail here, but I'm trying to give you a good overview. All of the information I'm sharing here is public information. I even, in order to force myself to make sure I didn't share private information, I went out on Wikipedia, memory vendors' websites, everywhere that I could find that's public to make sure that everything I wrote down is public. Just a quick overview, DRAM. All the memory technologies we're talking about for system memory today are DRAM. The DRAM memory cell, it's basically a capacitor, and you have a switch that lets you charge or discharge that capacitor. Well, capacitors leak. They don't hold their charge forever, and so you have to refresh it. And so when we talk about HBM, LPDDR, DDR5, it's all based on this same memory cell architecture. Why do we use DRAM if it leaks? Because you get probably on the order of at least 6 times the density than you get with SRAM. If you look at the CPU caches are built predominantly with SRAM, and you're getting hundreds of megabytes in some cases. So DRAM ends up being, for main system memory, still probably about the best compromise between performance, cost, and capacity. So when we look at it, HBM, it's built with these same DRAM cells. I took the picture to the right off of Wikipedia because it illustrates where HBM resides. HBM is inside the processor package. It's connected to the processor by connecting it to a silicon interposer. And this example is with a GPU. You could also do that with a CPU. And it's got DRAMs that are stacked on top of the controller die. Those stacks can go 8 high. We're starting to see some 12 high stacks. The specification allows for up to a 16 high spec in HBM3E. And so you get your capacity by growing the height of the stacks. The challenge that you get with HBM is I'm taking DRAM that is accustomed to run at 85 degrees C and putting it inside of a GPU package or a CPU package. And typically your CPU packages are rated to go closer to 100, 105 degrees C. And so now I'm expecting DRAM to perform in a CPU environment. And so there are various different error management schemes that are put in place by GPUs and CPUs. I don't have time to go into those, to ensure that the higher temperatures don't cause data degradation in such a way that it affects the operation of the system. So the bit rate on HBM varies by generation, and believe it or not, some generations of HBM run at a slower bit rate, but they get higher bandwidth by going to a higher number of pins at the lower bit rate. So over the life cycle, HBM started out with 512 bits, it's gone to 1024, and 2048 is coming in the future. One of the other challenges of HBM is it's capacity limited. Generally, what we're seeing today in stacks is about 32 to 36 gigabytes per stack. And most of the time in a CPU or a GPU, you're seeing 4 to 6 stacks. And so that gives you a feeling for how much total HBM you can have per processor or per GPU. And in a number of AI applications, the HBM is enough memory for the GPU, because then you do your overflow either into the CPU memory or into other memory areas. Okay, moving on to LPDDR. Now, if people have questions, I'm willing to stop in the middle or I'm willing to go to the end and then answer them then. LPDDR, the history for that is the mobile devices, phones, tablets, wanted a more power efficient memory because they're running on batteries and battery life is a major selling point. And so LPDDR was based originally, it was a derivative of a DDR, but they threw away features that didn't apply to a mobile environment. The other thing they threw away was the ability to put it onto a DIMM or onto a separate module and connect it via a socket. So all of the original LPDDRs were designed to be soldered down to the board. So now when we have the chip soldered directly to the board, that limits your flexibility. Once you buy the board, you've got as much memory as you'll ever get. And so LPDDR historically has not been very interesting to a server environment because most servers are designed to be general purpose. And when you take a general purpose server, you want to have memory sockets instead of memory soldered down to the board. You have probably seen there are various laptops out there that are built with LPDDR memory. LPDDR is becoming far more common in laptops. And what you'll find is the memory is not configurable in those laptop models. What you get when you buy it is what you get. Now, also because of the requirement to solder it down on the board, you're consuming a lot more physical board space than you do with a DIMM socket. And so simply soldering it down causes some limitations on the max system memory you can have. Now, LPDDR has started coming into the server arena, mainly with AI applications. And I heard someone mention NVIDIA's Grace Hopper. So the Grace CPU is using LPDDR memory. There are variants that have the LPDDR soldered down, and there is a new socket technology called CAM2. The JEDEC standard calls it CAM2. It's a compression connector. The unique thing about this socket is it has sufficient signal integrity to take a DRAM that was designed to not go through a socket to preserve signal integrity, and it can still be supported going through a CAM style connector. And so what you will see coming down the road in some of the NVIDIA designs and possibly in the future in other designs, LPDDR will come in a socket in a way that you can install it in sockets. And so one of the biggest challenges I see with LPDDR soldered down is if you solder it down to the same system board that you solder your CPU down to, now your CPU is being replaced at a DRAM failure rate. And typically a DRAM failure rate is much higher than a CPU failure rate. And so that's another reason why we have never wanted to go with LPDDR in a server environment, because I don't want to replace my CPU every time the LPDDR fails. Now, I will tell you, I can't tell you the details, but NVIDIA has done a lot of work into error correction and error management. They do not have the same level of error correction and error management as you get in a general purpose server that's based on the more traditional server chipsets. However, the error management is sufficient to the AI environment. In my discussions with various architects, I've told them that you need your memory protection to understand the cost of downtime. So if the cost of downtime is that someone dies, you're not going to use LPDDR. If the cost of downtime is somebody loses $1 billion, you're not going to use LPDDR. If the cost of downtime is that your AI application goes to 97.5 percent accuracy instead of 97.6, LPDDR is just fine because that's within the realm of accuracy that you expect out of an AI application. And so LPDDR, I don't see it coming into mainstream servers until we can find a way to improve the error correction capabilities of the LPDDR memory. So moving on to DDR. DDR is kind of the Swiss Army knife of memory. It is designed to be general purpose. It can run soldered down to system boards. It can run soldered to expandable memory modules. It can run on SODIMMs in laptops. It can run on RDIMMs in servers, UDIMMs in desktops. It is truly the general purpose memory. And like I say, it's a Swiss Army knife. It has good latency, good throughput. LPDDR is slightly higher throughput than DDR. HBM is way higher throughput. But with DDR, generally speaking, I can get much higher capacities. And because I am putting it on an edge connector type style, I can put a lot more DIMM sockets and then DIMMs on a server board than I can solder down LPDDR memory. And so the overall system capacities with DDR are significantly higher than the amount of capacity you get with LPDDR. It is configurable because it's on modules. So if you want a system full of 16 gigabyte DIMMs, you can put 32 16 gigabyte DIMMs in a system and away you go. If you want 8 terabytes in a system, you put 32 256 gigabyte DIMMs in the same exact system. And now you've got 8 terabytes of memory. And so the real beauty of DDR is it is true general purpose. Your system bandwidth is determined not so much by the bit rate of the DRAM, but by the number of DIMM sockets you can apply to the system board, how many memory channels those connect to, and the number of DIMM sockets. So DDR is really, its real benefit is its configurability and flexibility. So there is a new DIMM coming that is based on DDR5 technology, but it's called an MRDIMM, multiplexed rank. It provides about 20 to 30% higher throughput than an RDIMM using the same DRAMs as the RDIMM. What it is doing is it's using a buffer on the DIMM to interleave the reads to 2 different DRAMs all onto the same system bus at the same time. So if my DRAMs are running at 4400, the system memory bus runs at 8800, and it carries the payload from 2 different DRAMs at the same time. So a single thread is still going to get the data off of a single DRAM. So the data rate to a single thread isn't going to change, but now I can feed twice as many threads at that data rate in the same amount of time. And so MRDIMM really allows us to take and install higher speed DDR memory into a general purpose server. The biggest challenge with MRDIMM is it uses about 5 watts more per DIMM than the same capacity RDIMM. And so you're not going to want to use this for a general purpose workload that doesn't really need the bandwidth. But if you really truly need the bandwidth, MRDIMM is coming. The first variant of MRDIMM it predates the JEDEC specification. JEDEC is working on an MRDIMM specification, but it's not done yet. And so one of the system vendors, Intel, worked with the memory vendors to get a pre-JEDEC version of MRDIMM available. and you will see that one show up in the marketplace on the next generation Intel chips that are just launching now. I think they may have even publicly announced them. That support is there. AMD will support and other SoC vendors will support the JEDEC version. So here is just a quick technology comparison, and I put most of it in as qualitative because for example, latency, because they're all DRAM, the latency on all of these technologies is pretty good. MRDIMM, the power is highest, followed by HBM and DDR5, whereas LPDDR gives you the lowest power per gigabyte. The form factor on DDR5 and MRDIMM, they share the same DIMM form factor. They plug into the same DIMM socket. HBM, it's inside the CPU package. So if you choose the CPU or the GPU that has HBM in it, you've also chosen the HBM memory. And then LPDDR is solder down and CAM. And so really all of these are DRAM, but LPDDR and HBM are special purpose DRAMs, whereas DDR5 is general purpose. So which one is best for your application? It depends what your CPU uses. If you choose a Grace Hopper design, guess what? You're getting LPDDR. Your choice points have already been made when you choose Grace Hopper. The GPU will be using HBM. The CPU will be using LPDDR. If you were to, for example, choose an Intel Xeon, you're going to get DDR. The next generation Xeons that are just launching, MRDIMM becomes an option. So do I choose DDR5 RDIMM or MRDIMM? That's going to depend on where you get your best performance. Some applications get performance through capacity because you're taking data off of the hard drive and off of the I/O subsystem. Other applications depend more on memory throughput. So the memory capacity is enough, but you just need to get access to it a lot faster. So really those are your choice points between DDR5 and MRDIMM. And that is what I have prepared as a brief 20,000 foot overview of a multi-hour discussion. Does anyone have any questions?
Hi, thank you very much. What is consuming the extra 5 watts of power in an MRDIMM?
The buffer.
Okay.
By adding that buffer there, because the system side of the buffer is running at twice the speed of the DRAM. And to run it at that speed, you have to have much higher edge rates on the signaling in order to get a good data valid eye back at the CPU. And so you have to speed up the edge rates a lot, and edge rates are what consume your power when you're transferring data. Any other questions?
Yes, I got two questions. One is, why isn't the speed double in MRDIMMs? And my second question is, can I do a mix and match in a server? Can I add two MRDIMMs and two DDR, maybe in a different socket CPU?
Okay. The quick answer to number 2 is no. MRDIMM, the CPU vendors technically could, but if you're going to install MRDIMM, generally speaking, you want bandwidth and you're going to want it across all your channels. So the CPU vendors are not supporting mixing MRDIMM with RDIMMs. Why do I only get 30%? It's because on the first platform that supports MRDIMM, the RDIMMs are going to run at 6400. But when you plug in an MRDIMM, you're going to run at 8800 or 8000, depending on the platform configuration. And so on an 8800 MRDIMM, you've got DRAMs that are rated to run at 4400. And so basically, the system is designed the system designs are not ready yet for 12800. And so why put the 6400 DRAM on the DIMM and have the additional cost there? And so really it comes down to signal integrity at the system board level. 8800 is about all we can do on the system boards with today's technology. Next generation, we've got roadmap, we're working it, and the first JEDEC version is going to run at 12800 is the current target. And by then the system board technologies will have caught up to that.
Are street prices going to roughly land between DDR and HBM somewhere? Is that where they're going to, their performance is going to be between there and their pricing is going to be in that range?
It's hard to compare pricing because HBM, it's application specific, and the pricing of HBM is baked into the price of the CPU. So how much of that cost is HBM cost and how much of it is CPU cost and how did the CPU vendors build that out? They have not told me. When it comes to DDR versus MRDIMM, my expectation is MRDIMM will come in at a higher cost because you're adding additional chips to the DIMM, and those chips don't necessarily come cheap. It's not a few pennies each, it's more than that. But also it's pretty advanced technology to be able to multiplex that and get it to run at 8800. MRDIMMs across the industry will probably be much lower volume than RDIMMs, at least to begin with. So that's also going to be a piece of the pricing puzzle. Now, I will tell you, I am not the marketing guy, and so I don't look at pricing all the time. And so my answers are deliberately qualitative because I don't actually have the numbers.
Any last questions? Yeah.
Are there any plans to go further than 2x with MRDIMM? Could it be like 4x?
Okay, theoretically, something like that could be done. When the rubber meets the road, that's way too advanced for the system board technologies right now. And we'd be talking about if I put a 6400 DRAM, I'd be running at 24 gigabit per second as my bit rate. And for a DRAM bus that's a massively parallel bus, we are nowhere near that. That we may not even be able to hit that with the next generation of DRAM that will follow DDR5. And so we can only go as fast as the system board technologies can keep up with. And PCIe isn't even there quite yet. And DDR is a massively parallel bus that has a much different signal integrity profile than PCIe.
Eric, thank you very much. Thanks for stepping in at the last moment and doing this for us. It's greatly appreciated.
I hope it has been helpful.
Very much so.
My name is PJ Waskevich. I'm a Linux kernel engineer at Jump. I work with Sean. And I was asked to come in and talk a little bit about CXL and sort of how we view it within Jump, but also just in general. I also work on CXL as part of the CXL consortium. So also looking at this from an industry side of where I see this fit in and how it fits with the Linux kernel and the whole ecosystem. So as Eric also said, this is a much larger presentation that I've tried to boil down as much as possible. For the time, I'll try to hit on some very important points in my opinion. So I'll skip over some slides. Please do stop me though if there are questions. Otherwise, feel free to ask anything at the end. All right, so why I hope you're here is learning about what is CXL. I have no background as to what folks in the room know about CXL. If you guys are CXL experts or have no idea what it even stands for, we'll level set really fast. And talk about what it takes to use CXL. This isn't currently something that you just kind of pull out of the box, plug a bunch of stuff in, and poof, you're running with CXL devices. How it fits into Linux, that's again something that is very near and dear to my heart, how this works. And how does this also fit into sort of an HPC world? So CXL is stands for Compute Express Link, and it is a new protocol. Actually, specifically, it's a set of new protocols that run over an existing interconnect. Right. So this is something that whenever I do talk about CXL, I try to be very pedantic about. PCIe up until now, for what, the last decade and a half or so, has always described both the protocol and the physical interconnect. And so it's very confusing when you talk about CXL to people and they're like, but it's the PCI slot. I'm like, well, no, it's a physical slot that happens to fit a PCIe card that also talks PCIe and it can talk CXL. So it's something that mentally, I think the industry is going to have to come to terms with, that there's now this physical interconnect, PCIe form factor, but it can run these multiple protocols. As the protocol, it's driven by the CXL consortium. This is sort of like a cousin to the PCI SIG. We operate very similarly. In fact, there's a lot of people that are on both the consortium and the SIG. And just something to kind of, again, level set with PCI Express, PCIe root complex, where all of your peripheral devices flow through. That is the device that is memory coherent with your host and not peripheral devices. And that's very important, as you'll see in a second. So I mentioned that CXL is actually 3 different protocols, and they are CXL.io. This is effectively PCI Express. So if you were to look at a CXL FLIT, which is the datagram within CXL that is equivalent to a PCI Express TLP, CXL.io looks just like PCI Express. So you can see the MMIOs, the memory mapped IOs, reads and writes to memory, the DMAs, all of that traditional PCI Express flow. CXL.mem, which is, I think, what this room is probably going to be the most interested in, allows your peripheral device to be directly memory coherent with the host. And that's pretty cool if you start to think about some of the use cases that you might be able to bolt on with this, where you have memory on your device, like think GPU, and that memory is now part of the physical address space of your CPU. So your CPU and your applications running on your CPU can read and write directly to that memory, not have to go through some mapped aperture down into some shared memory segments, but more on that in a bit. And the third one, CXL.cache, this allows your device to be cache coherent with the host. So think of a CPU is running and sends a snoop for a cache line. Well, that cache line might be owned by your device, your peripheral device. And so your peripheral device needs to respond to the snoop. And so you can start also thinking about some really crazy use cases, and it can get pretty complex pretty fast. Yeah, and I already mentioned this, that CXL uses the PCIe PHY, uses the form factor, the electrical signaling, all of that, but it's a different protocol. Just to kind of further drill this in, if you see my laser pointer thingy here, this is just kind of a block diagram of how traffic would flow through a host between PCI Express or CXL. So in a device, typically that is CXL capable, there would be some arbiter that's down in the block, the PCIe CXL block that decides whether or not you train as PCI Express or CXL. And then once that happens, this MUX decides, are you PCIe or CXL.io? You go up through this traditional path. Otherwise, if you are cache or mem, you're going directly to basically the host CPUs. So it's a very simplified block diagram, but there are other block diagrams where this is flattened out and you can actually see your peripheral device kind of at the same level as the CPUs. Yeah. Now, not to, just because we like terms, this, I always joke that this came out of marketing because they needed to wrap something around the 3 protocols, because you start talking protocols to people that aren't terribly technical and then their eyes glaze over. So you like to talk about types. You like to talk about my device is a type 3. But it does sort of make sense. It helps sort of classify things into buckets of what are they capable of. There's type 1 devices, which I'm not going to really talk too much about, but basically it's a cache coherent device. It's an accelerator. There's type 2 devices, which are very interesting for many reasons. These are devices that are accelerators using the .mem and optionally the .cache protocols to accelerate data flows. So think of like a DMA, right? A host to card memory transaction. Today in PCI Express, I set up some DMA regions. I ring a doorbell. The hardware comes up and DMAs the stuff out of host memory and then shoves it out onto the wire. With a type 2, I can have a memory region that's set up in my device that is mapped into the host space, and my host can post those memory transactions, and I am now coherent with the host, and I see that there is now memory there, and I just pull it and go off and running. There's no doorbell, there's no DMA transaction, there's no credit, PCIe back pressure to worry about. I mean, there is at the protocol level, but it's hidden. So things like SmartNICs, things like GPUs, this is a really interesting use case that we're not quite seeing too many devices, but there's definitely rumblings about it. And then type 3, this is probably what, if you have heard of CXL, this is probably what you're most familiar with. This is also known as memory expanders or memory expansion. Think of you decom a whole bunch of servers and you have a bunch of DDR4 that was very expensive at some point, and it's still pretty relevant. Build a CXL enclosure, you shove a whole bunch of DIMMs into it, stick a CXL controller on the end of it, and plug it into your host, and poof, you have like 6 terabytes of attached memory that didn't before. That all sounds very easy, but it's a lot more complicated than that. Yeah, I'm not going to really drill into this, but the point to take away from this slide is that there are a number of specifications out. CXL 1.1, that is the current hardware that is shipping today, is compliant to CXL 1.1. So that's Intel's Sapphire Rapids, Emerald Rapids, AMD's Genoa. CXL 2 is coming in the next generation of Xeons and EPYC that should be shipping sometime this year. And then CXL 3 and 3.1, and 3.1 is probably where the intercept will be. That's like next, major microarchitecture generational, and that comes with PCIe 6. So the point to take away from here is the consortium has been cranking out specs with huge amounts of features, and the reality is the hardware that you can get your hands on today is nowhere near what the spec is able to provide. So there is some gap that we're having to play catch up and get up to some of these more advanced features. So one other thing that some people ask me, like, well, why the heck do we have CXL? Like, what was the driver? There's always got to be a good reason instead of just being a hammer looking for a nail. There are more and more requirements from people to try and build a device that could be memory coherent with the host or cache coherent with the host. There are other protocols that have come along and sort of died off because of CXL. So if you've heard of CCIX or C6, if you've heard of CAPI, from IBM, C6 was mainly driven by AMD, Gen Z was driven by HP. These were all kind of in what I call the protocol wars, and they sort of lost to CXL, but it made it very clear in the industry that there was a need. People were asking for, I want to do this. I want to be able to have a GPU with a crap load of memory that I can map into the host and then have direct access to it, or a SmartNIC or something else. So there really is a driver here for this. Yeah, and so where are we with the kernel? So, for those of you who are, deeply steeped in Linux, and play with, kernel mods or pull upstream kernels and test, the main focus has been on CXL2 and beyond. And there's a lot of reasons behind it. The main reason is CXL 1.1 was really kind of a stopgap where a lot of the support for CXL in the 1.1 spec comes from the BIOS or the platform firmware. So there's very, very little, if any, OS level interaction at that point. So you have to have a custom BIOS. You have to have a vendor that supports that, turns on all the crazy knobs. Your hardware that you design has to be very specific to follow that path. And CXL2 is where things get much more loose in terms of the OS can now actually control a lot of this stuff. So that's why the upstream maintainers have been very focused on that. There is QEMU support, so if you want to go and test what a CXL environment looks like, but you don't have hardware, you can go get that and emulate CXL host. So that's kind of slick. Okay, and then hardware. So there are emerging solutions. In my bigger presentation, I've got some examples of some vendors that have been kind of early to the party. One of which is Samsung, and like I'm in no way state or endorsing anyone or trying to plug anyone. It's just they've been out there. If you look up CXL memory expansion, you're probably going to get to a Samsung page. There's also another company in Fabrica. It's a startup that's like this Super NIC, which is CXL Fabric in it. So there's a lot of things coming out. Mostly is focusing on Type 3. If we remember our marketing slide from a few slides ago, that is the memory expansion. But the general purpose use case for CXL in terms of like an accelerator card has not emerged yet from a vendor. And I do think it's coming. It's just, again, what's in the spec versus what's in host hardware that we can get our hands on are two very different things. So this was actually something I did want to call out. So Meta had been playing around with this, and you can see this was actually a few years ago, where they posted some patches and they said, hey, we got CXL Type 3 memory expansion working in a CXL 1.1 environment, and then we did some latency measurements. And we wanted to see where does CXL attached memory fall into kind of the pyramid of latencies. And it actually turned out pretty good. So it turned out more or less to be an equivalent of like a farther NUMA node, which is pretty promising, right? If you have slower DIMMs that you're trying to repurpose, the latency of the DIMM, the CAS latency is sort of hidden by this, far memory fetch, which is really nice, right? Because now you can DPOM a lot of older hardware, harvest a lot of this stuff that's pretty expensive, and then continue to get value out of that depreciating hardware. And there's a lot more work that's happened since then on this memory pooling. There's some other standards trying to come along to like kind of wrap this into more of a consumable package. So yeah, so Type 3 devices, I think, are really the thing that you're going to see mostly people kind of gravitating towards, because it's a use case that you can kind of wrap your head around. I plug in a box full of memory with a CXL link in between, and I get more memory. That's pretty easy to kind of understand. SmartNICs, GPUs, things that are Type 2, where they start becoming coherent, especially at the cache level, that gets pretty complicated, because now your device needs to implement and understand the cache coherency protocols of the host CPUs. And if you've messed with or built a CXL device, trying to get a vendor to open up what their cache coherency protocol spec is to say it's a little difficult. So it's more of a pass fail. I try to do something, I send the wrong snoop, and then the system blows up, and then I go and talk to the vendor, and the vendor says, "Oh, don't do that." Okay, well then what do I do? So this has been definitely an area where CXL is not progressing fast enough, in my opinion. Yeah, so that's what I just said. CXL cache. It is very specialized, right? This is something that someone might come up with a generalization at some point, but not today. This CXL architecture focus shift is something I did want to mention. Is there was a lot of hype over the last few years for CXL. The specs were there, they were looking awesome. There's all these cool features. Then the hardware launches, and it's like, well, where's the rest of the specs? You know, the spec features. So some of the luster has kind of buffed off of CXL because there just isn't anything for people to put their hands on and get excited about. So I'm hoping that beyond 3.1, you know, we are working on 4.0 or what might become 4.0, that there isn't something like a readjustment of some of the technologies that are in CXL because like, hey, maybe no one's ever going to implement this, so we should just drop it. I haven't heard anything like that yet, and I'm pretty close to it, but it is something to keep in mind. So how does this kind of tie in with HPC, or how do I see it tie in with HPC? I see two very distinct use cases that make sense to me. In CXL2 and beyond, there's a concept of memory pooling, shared memory segments that can be actually shared across nodes. So a multi-host shared memory segment that's part of the protocol. So I'm sure HPC environments have their own bespoke frameworks to share memory segments across multiple nodes in your compute clusters. This would be a really nice replacement where you can focus more on your business logic of what you're doing with the shared memory segments instead of focusing on the undercarriage of trying to make your shared memory segments work. Or like what happens if a node crashes, what happens to that segment that it might be sharing. So CXL is going to really solve a lot of those issues. And then in like 3.1 and beyond, the CXL networking fabric becomes way more robust. So this, I think, is going to be a very interesting area for like traditional HPC compute that just needs a lot of memory shared across, you know, caches or storage across a lot of nodes. The other one is GPU acceleration. So I think once GPU vendors really start embracing CXL, see this as like a type 2 play that they can map their memory into host memory. They might be able to do some tricks with cache coherency. The AI ML compute or whatever the next hot thing past AI, I think this might really take off, where you have lots of GPUs in your data center, and then if they're now CXL capable, you can start to do a lot of other tricks to shave down latencies within the host and just get stuff working faster. And with that, I have successfully whittled down slides and went longer than I probably should have. So anyone have any questions?
PJ, thanks
Yes.
very much for being willing to jump on and talk with us. We really appreciate you taking the time. Anything?
Yeah, no, my pleasure. Thank you.
Anything before we let him go? Well, thank you.
All right. Have a great day, guys. Thanks.